Okay, in our last video we learned what is IEEE 754 32-bit floating point number representation, and again what is IEEE 754 64-bit floating point number representation. So in this video I'm going to teach you how to represent plus positive 43.125 using IEEE 754 32-bit representation. I'm going to show you how to represent this number in your computer using this particular method. Right, so let's take this number. Just forget about this plus thing. 43.125, right? So first of all, what do I have to do is I just have to convert this particular number into binary. So how do I convert this one into binary? So I have an integer part as well as I have a fractional part here. I just take these two separately, right? First take 43. So in order to convert 43 into binary, what do I have to do? I just have to divide by 2 until we meet a number below 2, which means 1, right? So let's divide 21 and 1 is remaining, and if we divide 21 by 2 we get 10 and 1 is remaining. If we divide 10 by 2 we get 5 and 0 is remaining. If we divide 5 by 2 we get 2 and 1 is remaining. If we divide 2 by 2 we get 1 and 0 is remaining. So we met a number which is below 2, right? So I'm going to write from here to here. So this is how to represent 43 using binary. So now let's convert the fractional part 0.2125 into binary. 0.125 into binary. In order to convert the fractional part, in order to convert the integer part into binary, what we did was we just divided it until we meet 1 by using 2. And in order to convert this fractional part into binary, what do I have to do? I just have to multiply this by 2. Here we divide by 2, here we multiply by 2. Right, if we multiply 0.125 by 2, we get 0.25 as the answer. So what do I have to do now is just take this value which is before the decimal point, right? We have 0 here. I just write this 0 here, right? So if we take a 0 from 0.25, the remaining value is 0.25. Now I'm multiplying again this by 2, right? If we multiply 0.25 by 2, I'm getting 0.5 here. So again, now I'm taking this value which is before the decimal point, I write it here, right? So if we reduce a 0 from 0.5, the remaining value is 0.5. Right, I'm again multiplying it by 2. So if we multiply 0.5 by 2, I'm getting 1.0. Right, if I write the value before the decimal point, I have 1. I write 1 here. So I'm reducing now 1 from 1.0. If I reduce 1 from 1.0, I'm getting 0. So we have to do this until we meet 0, right? So in here, the integer part we wrote here to here, but in this case we write from top to bottom, right? So now let's write 43.125. This is the decimal version. So how to write this one in binary? For 43, I have to write this 1011, right? So now I have decimal point, so I put binary point here, and again 125,001, I write this one here, right? So this is the binary version of 43.125, but the thing is how to, as I explained you earlier, we can only represent ones and zeros in our computer, but now we have a binary point here, which is a dot. So how to represent this dot in your computer, right? We have no way of representing this dot. Therefore, we have to remove this dot from this number. So in order to do that, what we do is, we call this process normalization. What do I have to do is just find the very first one that we have in our number, right? The very first one in your number, that is this one. After that very first one, just put the binary point, I mean 1 point, and just write all these things after that. 0 1 0 1 1 0 0 1. Right? What did I do is, I just took this binary point into this place after the very first one. Right? Now this is not the actual value. The actual value is this one. Now in order to take the binary point into actual place, I mean here we have to have the binary point. How many binary points I do need to jump? 1 2 3 4 5 binary point I do have to jump. Therefore I do write this like 2 to the power 5. Right? So this is what we call normalization. I'm repeating. So this number we can't store in our computer because of this binary point. Therefore I'm going to remove this binary point from our number. In order to do that, what I do is, I just take this binary point after the very first one in our number. Right? So after the very first one in our number, I just wrote like this, and all the rest of numbers I'm writing after the binary point. And to take the original number, I have to take the binary point 5 times right. So therefore I wrote like 2 to the power 5. So this part we call mantissa. So we have heard this word in our last video. So this one we called mantissa. So inside the mantissa part, I'm going to store this one, right? So this part we called exponent. So I'm not going to store exponent part inside our computer. I'm going to store the biased exponent in our computer. Therefore, the next step is to find the biased exponent. Right? So I have to find the biased exponent now. So how to find the biased exponent in 32-bit representation? I just add 127 into our exponent, right? What is the exponent now? 5 plus 127, I get 132. So we can't store this 132 in our computer because this is in decimal version. Therefore I do have to convert this one into binary now, right? So I'm then now converting this one into binary. Right, I get 6 and I get 66, right? And 0 is remaining. I just divide this one by 2, 33, and 0 is remaining. I just divide this by 2, I get 16 and 1 is remaining. 8 and 0, 4 and 0, and I again divide 2 and 0, 1 and 0. So this is the binary version of 132, right? So 132 equal 1 2 3 4 zeros and 1 00. So this is the binary version of 132. So this is the biased exponent now. Right? So now let's see how to represent the plus 33.125 using 32-bit IEEE 754 32-bit representation, right? So if this is IEEE 754 32-bit representation, I'm using 32 bits to represent your number, right? So as I explained you earlier, the very first bit is the sign bit, right? So in sign bit, what do I going to store? As this number is positive, I'm storing 0 here. If this was minus 43.125, I'm storing 1 here, right? So next 8 bits I'm going to use to store the biased exponent. Now I have already found the biased exponent here, 1 0 0 0 0 1 double 0, right? Let's see how many bits are there in this biased exponent. 1 2 3 4 5 6 7 8. We have exactly 8 bits, therefore I just write this one inside my biased exponent. Right, I wrote it inside the biased exponent, and again within this next 23 bits I need to store the mantissa, right? So what is mantissa now? Yeah, this one is the mantissa. 0 1 0 0 1 0 double 1 0 0 1. I wrote only 1 2 3 4 5 6 7 8 bits only. I used only 8 bits. I have 15 more bits remaining. I just fill all this 15 with 0, just right. So this is how to represent 30 plus 43.125 using IEEE 754 32-bit representation. This is how this value is stored inside our computer if you are using this standard, right? So I'm just ignoring this one. This one we are ignoring, right? So that's all.